Hello! In this video, we are going to discuss resonance structures. After this video, you should be able to define and explain resonance structures, recognize when a structure has resonance structures, and then draw all the resonance structures for a molecule. First, let's define what resonance is. What do I mean here when I say that if there is more than one allowed arrangement of molecules? What this means is that we are drawing the Lewis structure, and we are able to draw more than one that doesn't really break any rules. Now, if they are of equal stability, we call these equal resonance structures. If they are not equal in energy, they are called unequal resonance structures. In general chemistry, we tend to stick to discussions of equal resonance structures only, but as you move into organic, you'll often need to use less stable resonance structures to explain some reactions. Now, when we draw these, we draw each allowed structure and then use resonance arrows to indicate the resonance. Though we'll draw these as two or more different structures, in reality it isn't flipping back and forth between the structures, but rather it's an average of all of the structures. Now, let's look at some examples to help make this definition make more sense, and then we'll revisit it. Let's start with NO3-. We want to use our good habits of Lewis structure making, and so we'll count our electrons. We have 5 from the nitrogen, we have 6 from each oxygen, and we have 3 oxygens, plus 1 more for the negative charge. This gives us 24 electrons. Now we can draw out the structure and discuss resonance. So if we start with our pattern of drawing our skeletal structures, we have NO3 with the minuses around. And if you draw in your lone pairs, and you try to make an octet without adding any double bonds, you'll see that we don't have enough. We are short 2 electrons, because right now this would use up all of our electrons, but our nitrogen doesn't have an octet. So we need to add in 1 double bond here. Now the question becomes, which of these 3 oxygens should we add it to? And this is where the idea of equal resonance comes in, because there's no reason why you would add it to one versus the other. It makes no difference. And so for this one, I can go ahead and add it here, but I could have also added it to the other oxygens. And when you have that, you have equal resonance. And because in each of these cases, when you solve for your formal charges, you'll see that there is a -1 on one oxygen and a +1 on the nitrogen, and that's true for every single one of them. There's no reason why one is more stable than the other. And that's an example of equal resonance. And so we would draw resonance arrows between these. And in order to draw the correct Lewis structure, you would need to draw all 3 of these, right? If you just drew one, that's actually not adequately representing what is happening. And so you must draw all 3. Now, let's think about this in terms of the definition. If we move back to our definition slide, we said molecules have resonance if there are more than one allowed arrangement of electrons. And we see here that each of these 3 are allowed. We also were told that you cannot move atoms, just electrons. And you can see in each one of these, you're basically moving the 2 electrons from the double bond kind of around, and then the lone pairs to match. So we're not moving any atoms, we're just moving electrons. Now, we also said that in reality, the structures are a mix. So let's talk about this. Here we have 3 different ones drawn. But really what's happening is that it's a mix of all 3. So if we portray these a little more cartoony, it's not actually rotating between the 3. What's actually happening is you get this delocalized pi bond, is what we call it. So the electrons that are forming the double bond are delocalized across all 3 areas. And it's an average of those 3 structures. So again, that's called delocalized because the electrons aren't local to one bond, they're delocalized across all 3 bonds in this case. You'll also sometimes see it drawn with like dotted lines like this. That's okay, and in certain cases it makes sense to do that. It's not really a strict resonance structure, and it leaves out some information that's important. So when we ask you to draw a structure, we're asking you to draw what we did on this slide, where we have all 3 listed out, drawn out, and ideally you even really want to put the formal charges in as well. Now let's look at N2O. If we use our rules for drawing structures, we'd find these three structures. Using the standard rules of formal charges, where we want to minimize them, and then put the negative charge on the most electronegative species, this would mean that the first structure is the correct structure. And in general chemistry, we do tend to treat that as good enough. Either we have resonance that is equal, like in our previous NO3- example, or we pick the best structure. But as you move on into organic, you'll find that there are times when unequal resonance structures are needed to explain certain reactions and mechanisms. So though we won't go into this too significantly in this video, I just wanted to mention that in case this concept is important in your later classes. So hopefully now you are able to define and explain resonance structures, and then recognize when a structure has a resonance structure. From here, you can draw all the resonance structures for a molecule, and then if you are dealing with unequal resonance, state which is the most stable resonance structure.